Let's begin the second PowerPoint of design challenges for advanced nuclear reactors from PWR to Gen 4 designs. I'm Dr. Zafar Qureshi, professor at Air University, and this is part two of the PowerPoint. In this presentation, I'll take you through criticality, which is basically determining how much nuclear fuel, what enrichment, and what geometries it required in, then carrying out thermal hydraulics to determine how you're going to remove the heat from the reactor, what fluid you're going to use, what are going to be the flow parameters, and then carry out a structural analysis to determine whether it has stability. And that would require solving or simulating this in a multi-physics environment, basically using Hooke's law, the generalized Hooke's law. So a full multi-physics simulation would be carried out with a Neutronics code such as OpenMC and COMSOL or ANSYS. Here I'm going to take you through COMSOL for multi-physics, then discuss a little bit of point kinetics with you for determining the overall safety in a lumped reduced model. Okay, so the first step, as I mentioned, is to determine criticality. And this is a neutronics part of the entire simulation. So we begin, the easiest model that we are taught in university is the one group diffusion model in slab geometry, time dependent. And the next complexity comes in the one speed slab neutron transport equation, which is an integral differential equation here. Left-hand side outscattering, right-hand side inscattering, and an extraneous source. And the next model of complexity is the neutron transport equation, where the flux is a function of x, mu, and e. In a more detail, it would be a function of 7 independent variables. So here again, you can see an integral differential first order equation with the left-hand side showing the outscattering terms and the right-hand side showing the in-scattering terms. So to summarize this in the criticality part of the reactor design, you would you could use either the one group diffusion model, multiplying model, which is shown here, to estimate K, the multiplication constant. And in the easiest model, you've got nu sigma f and sigma a and the diffusion coefficient, and we can carry out a very crude basic analysis to estimate how big and what composition of fissile fuel you would require for criticality. In other words, for sustaining a chain reaction. And in a two-group better diffusion model, you could see the first group, the fast group, and the thermal group. And this is the relationship for k infinity for an infinite system, but we have a finite system, so we have the leakage terms over here, the fast leakage and the thermal leakage, and so that's how you would estimate. Now, this again we are taught in university in our first course on reactor physics, and then we go on to a multi-group diffusion where we carry out a numerical simulation using computer codes such as Anderson, Dot, Tridan, MCNP, Morse, OpenMC, Kenu, Triple E, etc., etc. Now, this shows you a plan view of a small micronuclear heat pipe reactor. The green is the beryllium oxide reflector. The drums uh, are rotatable absorber drums. The hexagonal monolithic core has red fuel elements, in this case uranium nitride, 70% enriched. It's a small reactor, with the blue being the heat pipes, which transfer heat out of the reactor, take it up to some Stirling engine or thermoelectric generator or any turbine system to convert thermal energy into mechanical into electrical energy. So in a typical Monte Carlo method simulation, you would be simulating the integral form of the Boltzmann transport equation, and going through millions of neutrons and estimating the neutron flux. And from the neutron flux, you would be able to get all the subsequent reaction rates, fission, absorption, in-scattering, out-scattering, group scattering, elastic, inelastic collisions, etc., to estimate the effective multiplication. Now, here I'm showing you tables from Devolpi, denaturing fissile nuclides. And for bare systems, for example, U-233, 235, and for plutonium 239, you can see the radius, the volume for an unreflected system, 48 kg, 5.8 centimeter, 18.9 grams per cubic centimeter. And as you put on a reflector, you can reduce. But these are very simple configurations. In a nuclear reactor, of course, it's much bigger. You've got nuclear fuel, and so the criticality calculations are necessarily much more elaborate and much more time consuming. Now, again from Devolpi, I'm showing you on the x-axis the enrichment and on the y-axis the mass for criticality. Of course, the less enrichment, the more mass you would require. So, uh, in a reactor, for example, you'd have 2, 3, 4, 5% uranium enriched. In a fast reactor, you could go up to 20%. In a micronuclear reactor, maybe 60, 70%. In a submarine reactor, maybe 90%. So these are the criticality estimates for some simple metallic and oxide configurations. Now let's move on from neutronics to thermal hydraulics, where you're producing heat and you have to remove the heat by some fluid flow. Fluid flow equations are the standard three conservation equations for conservation of mass, conservation of momentum, the three vector equations, and conservation of energy one. So we've got 1 plus 3 plus 1, 5 equations and the equation of state 6. So that closes the system which we need to solve for estimating all the flow parameters. Now heat, part of it would be conduction inside the fuel element. Q triple prime is the heat generated, and heat removed is by convection, uh, forced convection. So you would need empirical formulas such as the one I've shown here of Nusselt in terms of Reynolds and Prandtl numbers, the Ditters-Boelter equation. The complications partly arise from thermal conductivity, specific heat capacity, and all properties being functions of temperature. So you have to carry out a numerical simulation. Now, after the neutronics and thermal hydraulics, we have to look at the structural stability of the fuel because you don't want it to melt, you don't want it to crack. So you have to carry out something like a generalized Hooke's law form to uh, to calculate what kind of stresses and subsequent strains. Now look at this little pellet over here. It's changed its shape due to high temperatures and high thermal loading, of course, on the fuel element. So the stresses are the principal stresses, the Poisson ratio. This is for a cylinder R theta Z. Here's the thermal expansion, and here's the swelling and creep terms. The thermal stresses, in a very simplistic uh, calculation from Timoshenko, for example, you could see that it's a function of Young's modulus, thermal expansion, temperature gradient, and Poisson ratio. So this would be a first step to estimate the stresses. And from the stresses, what do we determine whether material failure is about to take place? We look at the stress strain curves, the proportionality limit, elastic limit, whether it's reversible, or whether we've yielded and moved on to the plastic limit. Now you know that for every material there is an ultimate failure where a material breaks, and that's what you have got to avoid. For stainless steel, for example, the yield strength for this particular stainless steel is 520 megapascals, and the ultimate strength is 860 megapascals. So in one of the failure theories, what we do is we calculate the von Mises stresses for the fuel rod and cladding. From the principal stresses, we calculate the von Mises stresses. We compare this with yield stresses to determine whether the material would yield and go from elastic to plastic to ductile. And remember that the yield stress is a function of. So here we see a typical stress strain uh, curve. This is for uranium dioxide, the fuel in pressurized water reactors. X-axis, the elongation, y-axis, the stress in megapascals. You can see here the proportionality limit, and here the offset yield strength, and then we move into the plastic limit, and eventually there's fracture stress over here. And all this is a function of temperature, so you've got to know how your material depends on your operating temperature. Okay, so by now you've gathered that we've done criticality, thermal hydraulics, and structures. So we've got neutronics, computation, reactor power, cell parameters, and we have to calculate the burn up. And from the burn up, we calculate the thermal hydraulics, the fuel temperature, the moderator temperature, and all these things are interconnected. And this is a simulation uh, for a code such as OpenMC, which is available, developed at MIT, now community uh, developed, and code such as ANSYS or COMSOL, where you can carry out this in a multi-physics environment. In the point kinetics, in the point kinetics calculations, you can see a lumped model where we determine the reactor power, and from there the thermal hydraulics, and we can carry out a safety analysis. This is by engineer just to show you that the criticality begins with a neutronic code such as OpenMC, and this is an open source particle transport code, fixed source, k eigenvalues, and depletion study. You these three studies. You have to create your input files where you specify materials, geometry, settings, and ask it, give it some optional input files. So basically, you'll get tallies such as flux and subsequent reaction rates, and you can plot them. Input files can also be generated using OpenMC's Python API. It's all very user friendly. So this is an example where you have the three geometry and materials and the simulation parameters here. And now typical results are shown in this black window where you've got K effective for collision estimator, track length estimator, absorption estimator, and a combined K effective. In this particular case, you can see 1.00069 plus or minus 0.00067. Now, a typical stochastic simulation would give you a mean plus a confidence level as a relative standard error to tell you whether your result is accurate and precise. Now, it could be precise and not accurate, so you want an estimate which is both accurate and precise. Now, this is a COMSOL multi-physics environment. You could use ANSYS, but in this particular case, COMSOL is being used uh, to uh, to carry out a multi-physics for thermal hydraulics and structures. And you can see that on the x-axis here, we've got temperature in Kelvin. On the y-axis, the height of the fuel rod. The coolant enters from the bottom, and as it travels upwards, its temperature goes up like that. So the coolant entrance and exit values are in this leftmost red curve. Then this is the clad outer surface, the clad inner surface, the fuel outer surface, and the fuel center line temperatures. So you can see that this is the highest temperature here. In this case, going um, above 1300 Kelvin. So remember, you have to look at the melting point, the safety margins that you've got in a pressurized water reactor, and you have to make sure that the maximum temperature you are operating at is within safety limits. Now, for that, you can look at Westinghouse's parameters, which you have to ensure for safety such as DNBR, the departure from nucleate boiling ratio, and other safety requirements. Now, finally, I'll come to point kinetics, which I told you is a lumped model. So you can see there are no spatial terms over here. These are four coupled ordinary differential equations, which are nonlinear when reactivity is multiplied by number density. So the first one is for number density, second for precursor concentration. This one tells you the reactivity as a function of time, ramp reactivity minus power feedback. So here's the Doppler term. There's a feedback over here. The fuel temperature depends in an adiabatic model on how much heat is accumulated. Now, for $3.5 reactivity input, you can see that as feedback effects become prominent, the reactivity drops. During this, you could have a burst, a power burst, in which a maximum peak power of this much is achieved, and the energy released is the blue figure here. Uh, so you could even go up in megawatts and in a burst. So it's important. Now, for this, there's a model called the Nordheim-Fuchs model, first done by Nordheim and Fuchs in 1946. It predicts the peak power and energy release in a fast burst meaning where the delayed neutrons can be ignored. And this is for a step reactivity insertion of $3.5 in an adiabatic model. And there are a number of models, and these days you've got artificial intelligence techniques, you've got machine learning, so you can train your system on generated data. You can use neurons, hidden layers, and you could obtain functions. For example, the neural network tool on MATLAB allows you to generate a function when you've trained the neural network on the data that you've provided. So that sort of ends my overview on criticality, neutronics, thermal hydraulics, structural analysis, burn-up and depletion, which is also a very important part, and accident analysis. So in criticality, you saw calculations give the K effective for cold and hot full power states as fuel and moderator temperature vary from startup to full power at high temperature. And you control the K effective by moving absorbers in and out. Neutronics, you need to compute the radial and axial power distribution, especially the thermal flux distribution to find where you've got peaking. You would like to have a uniform fuel burnup. So for that, you use variable fuel enrichment, shuffle it inside the core to maintain fuel and moderator temperatures that are desirable. You also need to calculate the feedback coefficients. In thermal hydraulics, you need to carry out a full thermal hydraulic simulation for fuel, cladding, coolant temperature, uh, distribution, axial and radial, to estimate the pressure drops. So you can estimate the pumping power, and you have to have a minimum departure from nucleate boiling ratio, which should be greater than 1.75. In structural analysis, you have stresses in fuel clad displacements due to thermal stress and creep. To ensure that the fuel does not touch the cladding, it does not rupture the cladding barrier, otherwise, fission products go into the coolant. And that's the protective layer which should not be violated. In burnup and depletion, because the nuclide density is changing, the fuel cycle length depends on it. So you need to estimate what is the maximum fuel burnup and what is the consumption of uranium and the production of actinides such as plutonium. And very important in thermal reactors are poison, samarium, xenon, etc. In accident analysis, you need to ensure that during your transients, you can use a point kinetics Nordheim-Fuchs model to estimate the energy released in a burst and to see whether that is within the safety. So here are the references, and I hope this lecture, it was just a bird's eye view of the various disciplines that go into reactor design. And of course, there's much more than this, but this gives you a first picture into this. Thank you very much.